happened without a word. No press conference, no alert, just a PDF quietly posted at 21:08 UTC on October 21st, 25. Inside, a single line that changed everything. Planetary Defense Network, active. Target, 3i Atlas. No one announced it. No one explained it. Yet the world's most powerful observatories were suddenly aligned, all watching the same object in the sky. Why the silence? Why this target? Something about this activation doesn't fit the script. It looks like training, but feels like preparation. Stay with me, because before the end, we'll uncover why NASA's quietest moment might be the loudest warning we've never heard. If these mysteries have you hooked the way they have me, don't just watch. Hit like and subscribe because you'll want to be here when the next piece drops. Tell me in the comments where you're watching from, what time it is, and whether you think we're getting the whole truth about these discoveries. And if you believe stories like this deserve daylight, share this video on X, Reddit, anywhere people still ask questions. This channel exists because of you, and thanks for always having our back. Part 1. The Claim. What NASA isn't telling you could be the most important silence in the history of planetary defense. Right now, as you're listening to this, a network of telescopes scattered across the globe is locked onto something moving through our solar system, something that came from somewhere else. And NASA activated its Planetary Defense Network to track it without a single press release. Let me say that again. The same planetary defense system designed to protect Earth from extinction-level asteroid impacts has been quietly mobilized to monitor an interstellar comet. No fanfare, no public announcement, just a single technical bulletin buried in the Minor Planet Center's catalog, designation MPEC 2025-U142, dated late October 2025. The object is called 3i Atlas. The 3i means third interstellar visitor ever confirmed. Atlas refers to the Asteroid Terrestrial Impact Last Alert System, the Hawaiian survey telescope that first spotted it. And here's what makes your spine tingle. This comet is now the subject of a coordinated observation campaign spanning from November 27th, 2025 through January 27th, 2026. There was a kickoff meeting on November 10th. There will be a wrap-up teleconference on February 3rd. This is not how astronomy usually works. When scientists discover something interesting, they hold press conferences. They issue glossy NASA press releases with artist renderings and excited quotes from principal investigators. They appear on morning news shows. Remember Oumuamua back in 2017? That Hawaiian name means scout, or messenger from afar arriving first. The scientific community went absolutely wild. Papers, speculation, even Harvard professors suggesting it might be an alien light sail. When 2i/Borisov arrived in 2019, the second confirmed interstellar visitor, we got updates, images from Hubble, media briefings explaining how this comet looked surprisingly normal despite coming from another star system. But 3i Atlas? Silence. Just a technical bulletin that reads like a shopping list. Observation window, kickoff date, participating observatories, wrap-up telecon. If you weren't specifically monitoring Minor Planet Center circulars, which almost nobody does except professional astronomers and obsessive amateurs, you would have no idea this is happening. Now here's where it gets interesting. This is the first time in human history that an interstellar object has been placed under a planetary defense level observation campaign. Not just casual monitoring, not just, hey, let's point a telescope at this interesting thing when we have spare time. This is coordinated, scheduled, globally synchronized observation involving multiple facilities across different continents. The kind of campaign typically reserved for potentially hazardous asteroids that might actually threaten Earth. Think about what that means for a second. The International Asteroid Warning Network, IAWN for short, exists for one purpose: to track objects that could hit us. Near-Earth asteroids with orbits that cross Earth's path. Comets that might fragment and send debris our way, objects that represent actual quantifiable risk to human civilization, and they just activated that network for an interstellar comet. Why would they do that? What could possibly justify mobilizing planetary defense resources for an object that by definition came from outside our solar system and is just passing through? These visitors have hyperbolic orbits. They're not bound to our sun. They arrive fast, swing around, and leave forever. They don't loop back. They don't pose long-term threat. Unless something is wrong with this one. The official explanation, buried in that same dry bulletin, is that this campaign represents a test of improved astrometry methods. Astrometry means measuring the precise positions of celestial objects. Improved methods means they're trying out new techniques, new calibration procedures, new ways of reducing measurement error. It sounds perfectly reasonable. It sounds like exactly the kind of technical exercise scientists would conduct. But if it were just a calibration test, would they really need to mobilize observatories in Hawaii, Chile, and potentially across both hemispheres? Would they need a formal kickoff meeting and a scheduled wrap-up teleconference? Would they dedicate 2 full months of precious telescope time, some of the most competitive scientific real estate in the world, just to test measurement techniques? Or is there something about 3i Atlas that has them concerned? Something unusual enough to warrant this level of attention, but not urgent enough or certain enough to trigger a public announcement? Here's what we know. The Minor Planet Center, which serves as the official international registry for asteroid and comet observations, flagged something in the data. Something about how 3i Atlas is behaving doesn't quite match predictions. Specifically, there are anomalies in its photometric behavior and centroid measurements. In plain English, the light coming from this comet doesn't align properly with where its predicted orbital path says it should be. That could mean a lot of things. It could be mundane measurement error. It could be atmospheric distortion affecting telescope readings. It could be the diffuse coma of gas and dust surrounding the nucleus playing tricks with the photometry, making the center of brightness appear offset from the gravitational center. Or it could mean this object is accelerating in ways gravity alone cannot explain. It could mean fragmentation. It could mean asymmetric outgassing, creating thrust like a natural rocket engine. It could mean the orbital models are wrong because scientists don't fully understand its mass distribution or density. It could mean something. Nobody wants to say out loud in a press release until they have better data. And that's what makes this silence so fascinating and so unsettling. Because uncertainty is often more alarming than confirmed danger. When institutions that normally embrace transparency suddenly go quiet, when they mobilize resources without explanation, when they schedule formal meetings and teleconferences for what they claim is just a calibration exercise, it tells you something. It tells you they don't know what they're dealing with yet, and until they know, they're not talking. So what aren't they telling us? Part 2. What we think it means. The International Asteroid Warning Network is not something you activate lightly. Understanding what ION actually does helps you grasp just how unusual this 3i Atlas situation really is. ION coordinates global efforts to detect, track, and characterize near-Earth objects that pose potential impact hazards. When I say potential impact hazards, I mean rocks from space that could actually hit Earth and cause regional devastation or worse. The network includes observatories, space agencies, and research institutions across multiple countries. It exists because asteroids don't respect national boundaries, and neither do their consequences. Typically, ION-level campaigns get triggered when an object meets specific criteria. Maybe it's coming unusually close to Earth. Maybe orbital calculations show a non-zero probability of future impact, even decades from now. Maybe the object is large enough that its trajectory uncertainty creates meaningful risk. These campaigns involve precisely coordinated observations, standardized measurement protocols, and rapid data sharing to refine orbital predictions and assess actual threat levels. 3i Atlas does not obviously meet those criteria. Its orbit is hyperbolic, meaning it came from interstellar space and will eventually leave our solar system entirely. Interstellar visitors don't threaten Earth the way near-Earth asteroids do because they're just passing through. They don't have the elliptical, sun-bound orbits that create recurring close approaches. Once they're gone forever. So why treat this one like a potential threat? The official framing, remember, is that this campaign tests improved astrometry methods. That phrasing is doing a lot of work. It suggests scientific advancement, technical refinement, the kind of incremental progress that happens constantly in astronomy. Nothing alarming about testing new techniques, right? Researchers always want better data, more precise measurements, reduced systematic errors. But here's the tension. If this were truly just about calibration, just about testing measurement protocols, you could do that with any convenient celestial object. Pick a well-studied asteroid with a precisely known orbit. Observe it repeatedly using your new methods. Compare results against established measurements. Validate your techniques. Publish a paper. That's how calibration exercises normally work. Mobilizing multiple international observatories for a 2-month coordinated campaign suggests something more urgent than routine calibration. It suggests the target itself matters. It suggests there's something about 3i Atlas that makes it specifically valuable or necessary for this particular test. Maybe because it's exhibiting behavior that current methods cannot adequately characterize. Maybe because understanding its anomalies requires pushing astrometric precision to new limits. Now let's talk about those anomalies, because they're genuinely strange. The bulletin mentions photometric and centroid measurement discrepancies. What does that actually mean when you're observing a comet? When you point a telescope at a comet, you're not seeing a solid object like an asteroid. You're seeing a fuzzy blob. The nucleus, the actual solid chunk of ice and rock, is typically tiny and invisible at interstellar distances. What you observe is the coma, a cloud of gas and dust sublimating off the nucleus as solar radiation heats it. This coma can extend thousands or even tens of thousands of kilometers. Inside that cloud, dust reflects sunlight, creating the brightness you measure. Photometry measures how bright that cloud appears. Astrometry measures where the center of that brightness is located. Under ideal circumstances, with a symmetric coma and accurate models, the photometric center, the brightest point, should align with the gravitational center predicted by orbital mechanics. You calculate where the nucleus should be based on gravity and past trajectory. Then you observe where the brightness peaks, and those two positions should match within measurement error. For 3i Atlas, they don't match well enough. The light is offset from where predictions say it should be. That offset could indicate several possibilities, none of them trivial. First possibility, asymmetric outgassing. Comets don't sublimate uniformly. Jets of gas can erupt from specific locations on the nucleus, perhaps where subsurface ice pockets breach the surface, or where darker material concentrates heat. These jets create thrust, actual physical force pushing the comet in specific directions. This non-gravitational acceleration changes the orbit in ways that pure Newtonian mechanics cannot predict without knowing the jet strength and direction. And if those jets are pointing the dust cloud predominantly to one side, the photometric center shifts away from the nucleus. Second possibility, fragmentation. Comets sometimes break apart, especially when stressed by solar heating near perihelion. If 3i Atlas has shed fragments, you might be observing multiple pieces close together, creating a complex brightness distribution that doesn't correspond neatly to any single gravitational center. Fragments can orbit each other, spread out along the trajectory or drift apart, slowly depending on how the breakup occurred. Third possibility, unusual density distribution or internal structure. If the nucleus has large voids, cracks, or highly uneven composition, its center of mass might not be where you'd expect from its overall shape and size. That mismatch would propagate through to brightness measurements if different regions outgas at different rates. Fourth possibility, the one nobody wants to invoke without extraordinary evidence. There could be something about this object's composition or behavior that doesn't fit standard comet models at all. Maybe interstellar comets formed under different conditions and behave differently than solar system natives. Maybe prolonged exposure to interstellar radiation altered its surface chemistry in unexpected ways. These scenarios exist on a spectrum from mundane to extraordinary. Science always prefers mundane explanations. But the fact that NASA and ION felt compelled to organize this specific campaign suggests the anomaly exceeds what can be easily dismissed as measurement noise or modeling error. If it were obvious calibration problems, they'd fix the calibration. If it were obvious model failures, they'd update the models. Instead, they're watching, closely, globally, in coordinated fashion, for 2 months. And they're not telling the public what they're hoping to learn or what they might be afraid they'll find. That calculated silence transforms routine astronomical observation into something that feels more like reconnaissance, more like surveillance of an unknown that refuses to behave according to script. What happens next depends entirely on what the data reveals, and whether anyone decides we deserve to know. Part 3. Timeline and Logistics. The campaign schedule tells its own story if you know how to read it. Kickoff meeting November 10th, 2025. Observation window opens November 27th. It runs continuously through January 27th, 2026. Wrap-up teleconference scheduled for February 3rd. Those dates aren't arbitrary. They're carefully chosen to capture 3i Atlas during a critical phase of its journey through the inner solar system. Comets brighten as they approach the Sun. Solar radiation heats the nucleus, increasing sublimation rates, expanding the coma, intensifying dust production. This brightening follows predictable patterns based on distance, composition, and nucleus size. Astronomers can forecast when a comet should reach peak brightness and how quickly it should fade afterwards. The observation window for 3I Atlas brackets the period when the comet is bright enough for detailed study, but also when its behavior becomes most active and potentially most unstable. Perihelion, the point of closest approach to the Sun, is the moment of maximum stress for any comet. Temperature gradients intensify, thermal expansion cracks the nucleus, volatile ices sublimate, explosively. If fragmentation is going to occur, perihelion is when it happens. The timing of this observation campaign suggests scientists want continuous monitoring through that critical period. They want to catch any changes in real time, not discover weeks later that something dramatic happened while nobody was watching. Why does continuous monitoring matter? Because cometary behavior can change rapidly. A single outgassing event lasting hours could alter the trajectory enough to throw off months of orbital predictions. A fragmentation event could split the nucleus into pieces that then evolve independently. If you're only observing occasionally, you miss the transitions. You see before and after snapshots without understanding the process connecting them. The global coordination aspect is equally important. Earth rotates. Any single observatory can only observe during its nighttime hours when the target is above the horizon. To achieve continuous coverage, you need observatories distributed in longitude. When Mauna Kea in Hawaii loses the target at dawn, facilities in Chile can pick it up. When Chile rotates into daylight, maybe observatories in South Africa or Australia can contribute. This follow-the-sun approach is standard for high-priority time-critical observations, but it's expensive in terms of telescope time. Observatories operate under competitive allocation systems. Astronomers submit proposals months or years in advance requesting specific observation windows for their research. Time is awarded based on scientific merit and feasibility. Coordinating multiple major facilities for a 2-month campaign requires high-level justification and institutional support. It requires convincing multiple independent directors that this target deserves priority over other worthy science. The kick-off meeting on November 10th presumably served to align all participating teams on protocols and expectations. Astrometry depends critically on calibration consistency. If different observatories use different reference star catalogues, different photometric filters, different reduction pipelines, their measurements won't combine cleanly. Systematic offsets between facilities can masquerade as real motion or brightness changes, so before starting everyone needs to agree on standards. What would that meeting have covered? Probably detailed observing strategies, which telescopes will observe when, what exposure times and filter combinations to use, how to handle weather contingencies when scheduled observations become impossible, how quickly to upload data to the central repository, what preliminary analysis each team should perform locally versus what gets centralized, who to contact if something unusual appears in the data that requires immediate follow-up or alert escalation. That last point is crucial. If 3I Atlas does something unexpected during the campaign, something that changes risk assessment or scientific interpretation, decisions need to happen fast. You can't wait for committees to meet. You need pre-established protocols. Who has authority to trigger additional observations? Who evaluates whether an anomaly is real or instrumental? Who decides if and when to issue public communications? The logistics also involve dealing with messy reality. Weather doesn't cooperate with observation schedules. Clouds roll in. Equipment malfunctions. Competing urgent targets like gamma-ray burst afterglows or supernova discoveries demand immediate attention, bumping scheduled programs. The moon's phases matter because bright moonlight drowns faint objects. Atmospheric conditions vary. Turbulence degrades image quality. All of these factors introduce gaps and noise into the data stream. That's why redundancy matters. Multiple observatories measuring the same object at overlapping times allows cross-validation. If one facility reports an unusual measurement, is it confirmed by others or is it an artifact? Independent confirmation is how you distinguish signal from noise. It's also how you build statistical confidence in subtle effects like non-gravitational acceleration, which might produce positional shifts of only a few arcseconds over weeks. As data flows back to the Minor Planet Center and E-ADUN coordination nodes, analysts begin iterative orbit refinement. Each new measurement constrains the trajectory slightly more. With enough measurements spanning sufficient time, you can detect patterns. Does the object consistently deviate from predictions in the same direction? Does the deviation grow stronger as the comet brightens, suggesting outgassing-related thrust? Or is it random noise that averages out with more data? Those refinements feed forward into forecasts. If the comet is accelerating non-gravitationally, models need to estimate how much that acceleration will accumulate over coming months. Will it remain negligible? Will it grow large enough to significantly alter where the comet goes next? Could it potentially change the trajectory enough to matter for future Earth proximity, even years from now? The wrap-up teleconference on February 3rd gives teams time to process the full dataset after observations conclude. Final orbit solutions get computed. Systematic errors get characterized. Scientific interpretation begins. Decisions get made about publication strategy and whether any of this warrants public communication beyond technical bulletins. And throughout all of this, the comet itself cares nothing for human schedules or concerns. It follows physics. Whatever is causing those anomalous measurements, whether mundane or extraordinary, continues happening regardless of whether anyone is watching. The campaign isn't changing the comet's behavior, it's only revealing what was already there. The question is what exactly that revelation will show. Part 4. Anomalous Behavior. Details. Let's get technical for a moment because the devil lives in these details. When astronomers say the light doesn't align with the predicted orbital path, they're describing a failure of two independent measurement systems to agree. One system calculates where an object should be based on gravity and past trajectory. The other system observes where the brightness actually is. Those should match. For 3i Atlas, they don't. The photometric centroid is where you measure the center of brightness. When you image a comet, you're capturing photons, particles of light reflected off dust or emitted by glowing gas. Modern telescopes use CCD sensors, essentially sophisticated digital cameras that count photons in each pixel. Software analyzes the image to find the brightest region and calculates its geometric center. That position gets converted to celestial coordinates, right ascension and declination, the sky's equivalent of longitude and latitude. Meanwhile, orbital mechanics predicts where the nucleus should be. You take previous observations, plug them into equations that account for gravitational forces from the Sun, planets, and even major asteroids if you're being thorough. You propagate the trajectory forward in time. This calculation tells you precisely where in the sky the object should appear at any given moment, down to fractions of an arc-second if your measurements are good enough. When the observed centroid doesn't match the predicted position, several explanations exist. The simplest is measurement error. Telescopes aren't perfect. Atmospheric turbulence blurs images. Sensor noise introduces random fluctuations. Calibration uncertainties in how you convert pixel positions to sky coordinates can introduce systematic offsets. Professional astronomers spend enormous effort characterizing and minimizing these errors, but they never disappear entirely. However, measurement errors are usually random. They scatter around the true value. If you take enough measurements, they average out. What's concerning about 3i Atlas is apparently consistent deviation, a pattern rather than noise. That suggests something physical is happening. Non-gravitational acceleration is common for comets. As ice sublimates, gas molecules shoot off the nucleus at high velocity. Newton's third law applies. Every action has an equal and opposite reaction. The outgassing creates thrust, like a leaky rocket engine. If this thrust is symmetric, pushing equally in all directions, it might not change the orbit much. But cometary nuclei aren't spherical or homogeneous. They're irregular chunks of ice and rock with varying composition. Outgassing jets often emerge from localized active regions. These jets can create significant thrust vectors. The famous comet 67P/Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission, exhibited dramatic jet activity from specific locations. Those jets changed the comet's rotation rate and orbit in measurable ways. Rosetta observed this directly, watching jets erupt and tracking the resulting motion changes in real time. For 3i Atlas, nobody has a spacecraft there. We're watching from hundreds of millions of kilometers away. We can't see individual jets. We can only infer their existence from the cumulative effect on motion and the asymmetry they create in the brightness distribution. If powerful jets are pushing dust predominantly to one side of the nucleus, the visible coma becomes lopsided. The photometric center shifts toward wherever the most dust accumulates, which might not be where the nucleus actually is. Fragmentation adds another layer of complexity. When a comet breaks apart, you suddenly have multiple pieces, each potentially outgassing independently, each on slightly different trajectories. From a distance, if the fragments remain close together, telescopes might blend them into a single fuzzy blob. The measured centroid would then represent some weighted average of multiple brightness peaks, which wouldn't correspond to any single gravitational center. Historical examples exist. Comet 73P/Schwassmann-Wachmann. 3 fragmented spectacularly during its 2006 apparition, splitting into over 60 pieces. Comet Shoemaker-Levy 9 famously broke into fragments before colliding with Jupiter in 1994. Fragmentation happens, it's not rare. But detecting it early, especially for a distant faint object, requires careful observation. Could 3i Atlas have fragmented already? Possibly. The anomalous photometry might be the first hint. If fragments exist, continued observations during the campaign should reveal them as the pieces slowly separate and become individually resolvable. That might be one goal of this intensive monitoring. Not just tracking the main body, but searching for evidence of pieces that could explain the brightness anomalies. Internal structure matters too. Cometary nuclei aren't solid blocks of ice. They're more like rubble piles, loosely bound aggregates of smaller chunks with significant void space. This porosity affects heat conduction and outgassing patterns. A nucleus with large internal voids might outgas asymmetrically as heat penetrates to buried ice pockets. The resulting mass distribution could be significantly offset from the geometric center, causing the gravitational and photometric centers to genuinely differ. Interstellar comets add another variable. These objects formed in other star systems under potentially different conditions. Maybe their composition differs from solar system comets. Maybe they contain more exotic ices with different sublimation temperatures. Maybe prolonged exposure to cosmic rays during millions of years in interstellar space chemically altered their surfaces in ways that affect how they respond to solar heating. We've only studied 2 confirmed interstellar objects before 3i Atlas. Oumuamua was bizarre, tumbling oddly and accelerating slightly without obvious cometary activity. Some scientists proposed it might be an iceberg of solid hydrogen or nitrogen, ices that don't exist in our warmer solar system. 2i/Borisov looked more conventional, behaving like a typical comet with normal dust and gas production. 3i Atlas is only the 3rd data point. Sample size 3 is too small for robust statistics. If it behaves strangely, we can't yet say whether that strangeness is common for interstellar visitors or unique to this particular object. That uncertainty compounds the interpretation challenges. Are we seeing normal cometary behavior we just haven't modeled well? Or are we seeing something genuinely unusual that demands new physics? The campaign aims to answer these questions through brute force. More data, better precision, continuous coverage. If the anomaly is real, detailed monitoring will characterize its evolution. If it's instrumental error, careful calibration will make it disappear. If it's outgassing, the pattern should correlate with brightness changes. If it's fragmentation, pieces should become visible. But until that data gets processed and analyzed, all we have are questions and a silence that feels increasingly deliberate. Part 5. Why the secrecy and quiet mode. Here's what makes the silence strange. NASA loves press releases. Space agencies in general love public engagement. When you discover something cool in space, you tell people. It's how you maintain public support, justify budgets, inspire the next generation of scientists. Astronomy has always been a public-facing science. We point at the sky and say, look at that amazing thing, and people look and feel wonder. So why not for 3i Atlas? Why no press conference announcing the first interstellar object ever placed under planetary defense monitoring? Why no quotes from excited astronomers explaining what makes this comet special? Why no artist conception showing its trajectory through the solar system? These are standard tools of science communication, and they're conspicuously absent. One explanation is scientific caution. Researchers hate being wrong publicly. If you announce something dramatic and it turns out to be measurement error or misinterpretation, your credibility suffers. Better to wait until you have solid data and peer-reviewed results before making claims. This conservative approach is how science maintains trust. You don't cry wolf, you don't oversell preliminary findings, you wait for confirmation. That principle makes sense for most discoveries, but this isn't a discovery announcement. Nobody is claiming 3i Atlas will definitely do anything unusual. The campaign itself is just monitoring, observation, data collection. You could announce that without making dramatic claims. You could say we're conducting intensive observations of an interstellar comet to test improved measurement techniques and better understand its behavior. That's factual, not speculative. It invites public interest without risking embarrassment if nothing remarkable emerges. The fact they chose not to do even that suggests institutional discomfort with attention. Maybe internal discussions raise concerns about how the public might react to the phrase Planetary Defense Network activated for interstellar object. Those words together create alarming implications regardless of actual risk level. Media coverage might sensationalize. Headlines might scream NASA tracks mystery object or interstellar comet defies predictions. Even if scientists carefully explain there's no danger, once fear enters public consciousness, it spreads faster than corrections. Institutional risk aversion makes people prefer saying nothing over saying something that might be misunderstood. You can't be criticized for statements you never made. If the comet turns out to be perfectly normal, the quiet campaign just becomes a footnote in technical literature, noticed only by specialists. No harm done. But if you'd issued press releases and organised media briefings, you'd look foolish explaining why you mobilised resources for something mundane. There's also the question of internal uncertainty. Maybe scientists themselves don't agree yet on how significant the anomalies are. Maybe some think the photometric offsets indicate real interesting physics, while others think it's just calibration issues. Until consensus emerges, institutions often default to silence rather than presenting confused or contradictory messages publicly. Contrast this with how previous near-Earth asteroids have been handled when they showed potential Earth impact risk. Asteroid 2004 MN4, later named Apophis, briefly showed a small probability of impacting Earth in 2029. NASA immediately issued statements explaining the risk level, how probabilities would be refined with more data, and why there was no immediate cause for alarm. Transparency served to prevent panic by giving people accurate information. Asteroid 2013 TV 135 wasn't detected until it had already passed Earth at a very close distance, inside the Moon's orbit. That triggered discussions about detection capabilities and monitoring gaps, but again, NASA communicated openly about what happened and what it meant for planetary defense improvements. When institutions handle potential threats with transparency, even uncertain threats, public reaction generally stays rational. People can handle being told we're not sure yet, but we're monitoring it and will keep you informed. What breeds anxiety in conspiracy theories is silence combined with leaked hints that something unusual is happening. And that's exactly what we have with 3i Atlas. No official announcement, but technical bulletins accessible to anyone who knows where to look. Amateur astronomers can read about the campaign. They can potentially observe the comet themselves if they have adequate equipment. Information exists but isn't being actively communicated. That gap invites speculation. Online astronomy communities thrive on finding things professionals aren't talking about. Forums, social media, amateur observer networks all trade information and theories. When something unusual happens without official explanation, those spaces fill the void with their own interpretations. Some will be reasonable, some will be wildly speculative, a few will be outright conspiratorial. Maybe that's acceptable to the institutions involved. Maybe they'd rather have fringe communities speculating than mainstream media sensationalizing. Fringe speculation reaches smaller audiences and carries less credibility. As long as major news outlets aren't covering it, the story remains contained. Or maybe the silence has nothing to do with public relations and everything to do with scientific process. Maybe researchers simply don't have anything definitive to report yet and see no reason to announce that they're collecting data. From their perspective, this might be routine work, interesting, but not extraordinary. The campaign structure might feel unusual to outsiders, but perfectly normal to insiders who regularly coordinate observations. Still, the combination of Planetary Defense Network activation and zero public communication creates a perception gap. It looks like something is being hidden, whether or not anything actually is. And perception matters because it shapes how people will react if and when information eventually does become public. If scientists conclude 3i Atlas is behaving normally, and the campaign successfully tested their methods. They'll publish results in technical journals and maybe issue a brief press release saying, "Mission accomplished, techniques validated, nothing to see here." Most people will never hear about any of it. But if the comet does something genuinely unexpected, if the data reveals behavior that challenges current understanding, then the silence leading up to that revelation will be scrutinized. People will ask, why weren't we told earlier? They'll wonder what else might not be communicated until after the fact. Trust, once damaged, is hard to rebuild. For now, the telescopes keep watching, the data keeps accumulating, and the questions keep growing in the space where answers should be. Part 6. Interstellar Objects. Precedence and Context. We need to talk about what came before because 3I Atlas isn't arriving into a vacuum. It's the third confirmed interstellar visitor we've detected passing through our solar system. The first two taught us that visitors from other stars are probably common and that they can be profoundly strange. Oumuamua appeared in October 2017. The Pan-STARRS telescope in Hawaii spotted it. The name is Hawaiian, meaning scout or messenger coming from the distant past. Initially categorized as a comet, then reclassified as an asteroid, then ending up in its own category because it fit neither profile comfortably. Oumuamua was weird from the beginning. Its shape, inferred from how its brightness varied as it tumbled, suggested something extremely elongated. Maybe cigar-shaped, maybe pancake-flat, but definitely not a typical roughly spherical asteroid or potato-shaped comet nucleus. It tumbled oddly, rotating in a complex way, and most bizarrely it accelerated slightly as it left the solar system. Not much, just a tiny anomalous push that couldn't be explained by gravity alone. Comets accelerate due to outgassing, but Oumuamua showed no visible coma, no tail, no detectable gas or dust emission. So what pushed it? Scientists proposed various explanations. Maybe it was outgassing something invisible, like pure hydrogen or nitrogen that don't create visible tails. Maybe radiation pressure from sunlight acting on its unusually shaped surface. Maybe it was a fragment, a shard of something larger that broke apart. Then one Harvard astronomer, Avi Loeb, suggested it might be artificial. An alien light sail, a piece of technology designed to be pushed by starlight, accidentally drifting through our system. That hypothesis generated enormous controversy. Most scientists found it implausible given the lack of evidence for non-natural origins. But the possibility, once raised, captured public imagination. Was Oumuamua an alien spacecraft? Probably not. But could we absolutely rule it out? Not with certainty. The key lesson from Oumuamua was that we don't understand interstellar objects well enough yet. Our models are built on solar system objects. When something from outside arrives, it can violate our expectations, and we barely got to study Oumuamua. By the time astronomers realized how unusual it was, the object was already leaving, too faint for detailed follow-up. We missed our chance. 2I/Borisov arrived in August 2019, discovered by amateur astronomer Gennady Borisov from Crimea using a homemade telescope. This one looked much more normal. Definite comet, clear coma and tail, outgassing behavior matching expectations. Chemical analysis of its spectrum showed familiar molecules, carbon and nitrogen compounds similar to solar system comets. It looked like comets elsewhere in the galaxy aren't fundamentally different from ours, but even Borisov had surprises. Its coma had unusually high concentrations of carbon monoxide compared to typical solar system comets. Its nucleus might have been more porous or fragile. Some observations suggested it might have undergone fragmentation during its visit, possibly breaking into at least two pieces. These weren't dramatic deviations, but they hinted that even normal-looking interstellar comets have subtle differences. The other lesson from Borisov was how much more we can learn when we're prepared. Because astronomers detected it months before its closest approach to the Sun, there was time to organize coordinated observations. Hubble Space Telescope observed it multiple times. Ground-based telescopes worldwide tracked it. Spectroscopy characterized its composition. Photometry monitored its brightness evolution. We extracted far more science from Borisov than from Oumuamua simply because we had more time. Now 3I Atlas becomes the third data point. And here's what's unsettling. Each of the three has been different. Oumuamua was bizarrely shaped and accelerated mysteriously. Borisov looked conventional but had compositional quirks. 3I Atlas exhibits photometric anomalies that aren't yet explained. With a sample size of 3, We can't identify what's normal and what's exceptional for interstellar visitors. That uncertainty matters for planetary defense. If interstellar objects commonly misbehave in ways our models don't predict, they become harder to characterize and potentially harder to assess for risk. If you can't accurately predict where a comet will be, you can't confidently rule out future Earth proximity scenarios. You need bigger error bars on your forecasts, wider uncertainty margins. The fact that 3i Atlas is receiving planetary defense-level attention suggests maybe the community has decided to treat interstellar visitors differently going forward. Not as exotic curiosities for academic interest, but as potential unknowns requiring careful monitoring. That would be a significant policy shift driven by lessons from Oumuamua and Borisov. If these objects can behave unpredictably, better to watch them closely than assume they're harmless just because they're passing through. There's also a statistical question. How common are interstellar visitors? We've detected 3 in 8 years, but detection depends heavily on survey capabilities. Pan-STARRS and Atlas telescopes are relatively new and specifically designed to scan the entire sky repeatedly looking for transient events. Before those systems came online, we probably wouldn't have detected interstellar objects unless they came extremely close or were unusually bright. Based on current detection rates, estimates suggest dozens or hundreds of interstellar objects pass through the inner solar system every year. Most go unnoticed. Some are too faint, some move too fast. Some arrive during times when telescopes are pointed elsewhere. The 3 we've found are likely just the tip of a much larger population. If that's true, if interstellar visitors are common, then developing robust protocols for detecting, characterizing, and assessing them becomes a necessity rather than academic luxury. You can't treat everyone as a unique special case requiring ad hoc responses. You need standardized procedures, established observation strategies, pre-coordinated resources ready to deploy when the next one arrives. Maybe that's what the 3i Atlas campaign represents, a prototype for future interstellar visitor monitoring. Use this object as a test case to develop and validate the methods you'll apply systematically to future detections. If that's the goal, it explains the coordination, the formal kickoff meetings, the scheduled wrap-up teleconference. You're not just studying this specific comet, you're building institutional muscle memory for handling the next 50. But that still doesn't fully explain the silence. If this is a prototype monitoring system, why not announce it? Why not frame it as a positive step forward in planetary defense capabilities? The public generally supports space safety initiatives. Demonstrating competence and preparedness builds confidence in institutions. Saying we're testing new methods on an interstellar comet to improve our ability to track unusual objects sounds responsible and forward-thinking. Unless there's something about this particular object that makes them cautious about drawing attention. Something in those anomalies that hasn't been ruled out yet. Something that would sound alarming if mentioned publicly before being thoroughly understood. Or maybe the 3i Atlas campaign is indeed routine and unexceptional to the professionals involved, and I'm reading significance into patterns that aren't there. Maybe the absence of press releases means nothing more than nobody thought this warranted one. Scientists are busy. Public relations takes effort. Not everything gets announced. But the ion activation still nags. That network exists for specific purposes. Using it for what's officially described as a calibration exercise stretches its mandate. And stretching mandates without explanation is how institutions drift into less transparent operations. Small decisions accumulate. Each quiet campaign establishes precedent for the next. Eventually, you have an entire monitoring apparatus operating without public visibility or oversight. And we circle back to the fundamental question hanging over this entire investigation. What aren't they telling us? Not necessarily because they're hiding danger, but because they're still trying to understand something that doesn't fit neatly into existing frameworks. Because uncertainty is uncomfortable, and institutions default to silence when they can't provide confident answers. Because saying we don't know yet feels like admitting weakness. But we're about to learn whether silence was justified, or whether it was simply habit, institutional inertia, the path of least resistance when faced with something that might be interesting but probably isn't. The telescopes will keep collecting photons. The data will either converge on boring explanations or diverge into genuine mystery. And either way, 3i Atlas will eventually be just another object in the catalogue, its moment of scrutiny reduced to technical papers and forgotten bulletins, unless it's not. Unless it becomes the one they'll reference years from now when explaining why protocols changed, why transparency improved, why we started taking interstellar visitors more seriously. Time will tell, but time is exactly what we're running out of as the observation window closes and February 3rd approaches. Part 7. Astrometry Challenges and Improved Methods. Let's talk about measurement, because understanding how difficult these observations are helps clarify what improved astrometry methods might actually mean. Measuring the position of a star is relatively straightforward. Stars appear as point sources, tiny dots of light. You determine which pixel in your camera image is brightest, apply calibrations to convert pixel coordinates to sky coordinates, and you have a position. Accuracy depends on your telescope quality, atmospheric conditions, and calibration. But the process itself is conceptually simple. Comets are not point sources. They're extended fuzzy objects, clouds of gas and dust that can span thousands of kilometers. Somewhere inside that cloud is a tiny solid nucleus, but you typically cannot see it directly at the distances involved. Instead, you're measuring the brightness distribution of the entire coma and trying to infer where the center should be. This creates multiple sources of error and ambiguity. First, the coma isn't usually symmetric. Outgassing jets preferentially emit material in certain directions. Solar radiation pressure pushes dust grains away from the sun, creating asymmetric tails. Viewing geometry matters because you're seeing a three-dimensional structure projected onto your two-dimensional detector. The center of that projection depends on which direction you're looking from. Second, brightness depends on particle size and composition. Tiny dust grains scatter light differently than large chunks. Gas molecules emit light at specific wavelengths when solar ultraviolet radiation excites them. If you observe through different filters, you see different components dominating. The photometric center measured through a dust-sensitive filter might differ from the center measured through a gas-sensitive filter, because dust and gas distributions aren't identical. Third, comets change rapidly. Outgassing rates vary with solar heating, which changes with distance and local day-night cycles on the spinning nucleus. Brightness can fluctuate significantly over hours or days. The coma expands and evolves. If you observe the same comet on consecutive nights, it might look noticeably different. This temporal variability makes it hard to establish a stable astrometric reference. Fourth, atmospheric distortion affects observations. Earth's atmosphere bends starlight through refraction. The amount of bending depends on wavelength, so different colors get deflected slightly differently. This chromatic effect means the apparent position of an object shifts depending on which filter you use and how precisely you calibrate for atmospheric dispersion. For point sources, this is manageable, but for extended objects with complex spectra, corrections become more difficult. Fifth, telescope instrumentation introduces systematic errors. Each detector has biases, hot pixels, sensitivity variations across the field of view. Optical systems have aberrations that distort images differently at different locations. Tracking systems have imperfections that cause slight drift during exposures. All of these effects need characterization and correction, but residual errors always remain. So what could improved astrometry methods entail? One approach is better calibration standards. Instead of relying on relatively sparse star catalogues for reference positions, you could use denser catalogues with more precise positions. ESA's Gaia mission has measured positions for over 1 billion stars with unprecedented accuracy. Leveraging Gaia data as your astrometric backbone immediately improves your measurement precision. Another approach is algorithmic improvement. Machine learning algorithms trained on large datasets can learn to recognize and correct systematic errors that traditional methods miss. You feed the algorithm thousands of images of known objects, let it learn patterns in how measurements deviate from true positions, then apply those learned corrections to new observations. This works especially well for complex cases like comets, where classical geometric corrections struggle. Multi-wavelength coordination helps separate dust from gas contributions. If you observe simultaneously through multiple filters capturing different emission and reflection components, you can computationally disentangle the brightness contributions and determine separate centroids for each. This gives you additional information about coma structure and helps identify which centroid best represents the actual nucleus position. Shorter exposure times, taken more frequently, trade signal-to-noise ratio for temporal resolution. Instead of one long exposure that integrates over hours of changing coma structure, you take many shorter exposures and analyze how the brightness distribution evolves. This lets you track rapid changes and potentially identify periodic variations linked to nucleus rotation or jet activity cycles. Coordinated simultaneous observations from multiple observatories provide parallax information and reduce random errors. If 3 telescopes in different locations measure the same object at the same time, you can triangulate its position more precisely than any single measurement allows. You can also identify which measurements are outliers caused by local instrument or atmospheric problems rather than real object behavior. The 3i Atlas campaign likely incorporates several of these approaches. The coordinated multi-site observations suggest they're using redundancy and parallax. The emphasis on improved methods suggests new algorithms or calibration strategies. The 2-month duration provides temporal baseline to track how anomalies evolve and whether they correlate with brightness changes that would indicate outgassing-driven effects. Why test these methods on 3i Atlas specifically? Possibly because its anomalies provide a challenging case that pushes techniques to their limits. If your improved methods can accurately measure a comet that's misbehaving, they'll certainly work on more conventional objects. It's like stress testing software by running it on the most difficult inputs. If it handles edge cases, it's robust. There's also potential value in demonstrating capability. If NASA and Yaun can show they successfully characterized a difficult interstellar comet using new techniques, that builds confidence in their ability to handle future unknown objects. It provides evidence for funding agencies that planetary defense investments are yielding tangible improvements in operational capabilities. It shows international partners that coordination works and produces better science than isolated observations. The methods validated here could feed forward into future survey systems. Next-generation telescopes currently under development, like the Vera Rubin Observatory's Legacy Survey of Space and Time, will detect vastly more small bodies and transient objects than current systems. Many of those objects will be faint, distant, and challenging to characterize. Having proven algorithms and protocols ready to deploy immediately when unusual objects appear will maximize scientific return and risk assessment accuracy. In that sense, the 3i Atlas campaign might represent a transitional moment. We're moving from an era when interstellar visitors were rare novelties to an era when they're routine detections requiring systematic response. The methods developed now become the standard procedures applied automatically to future cases. What feels like a special unusual campaign today becomes tomorrow's normal operations. But that transition depends on success. If the campaign conclusively resolves the anomalies and demonstrates improved astrometric accuracy, it's a win that justifies the investment. If the anomalies persist despite exhaustive observation, it suggests either the techniques need further refinement or the object is genuinely exhibiting behavior that current methods cannot adequately model. And if the latter, we're back to the uncomfortable space of not understanding something that's already inside our solar system and not behaving according to expectations. That's the scenario that makes silence feel less like caution and more like avoidance. Part 8. Hidden Hypotheses and Conspiratorial Angles. Now we enter speculative territory where evidence thins and imagination fills gaps. What if there's more to this silence than scientific caution? What if the anomalous behavior hints at something nobody wants to discuss publicly until they're absolutely certain? Let's explore possibilities that range from plausible but uncomfortable to outright fringe. Start with the simplest alternative hypothesis: hidden fragmentation. Comets break apart all the time, but usually we detect it because fragments separate enough to become individually visible, or because brightness suddenly increases as fresh, icy surface gets exposed. What if 3i Atlas fragmented subtly, creating pieces that remain close enough to appear as a single diffuse blob but separated enough to create complex gravitational and brightness interactions? Small fragments orbiting each other would create periodic variations in the overall brightness distribution as they eclipse each other or change their relative positions. The measured photometric centroid would shift in complex patterns that don't match simple orbital predictions for a single object. You'd see exactly the kind of anomalies described. Light not aligning with predicted path because you're actually looking at a mini-cluster pretending to be one object. This scenario is physically plausible and not particularly alarming. It's interesting science but not threatening. Yet it might be tricky to confirm without extremely high-resolution observations that separate individual fragments. If scientists suspect fragmentation but can't prove it yet, they might prefer waiting for confirmation before announcing it, because claiming fragmentation without evidence would be embarrassing if later disproven. Now escalate the speculation. What if one or more fragments are on trajectories that differ significantly from the main body? Fragmentation events impart velocity changes. If a piece broke off violently, perhaps driven by sudden outgassing or structural collapse, it could be on a path that differs enough to matter, maybe even a path that comes closer to Earth than the main comet. That scenario introduces planetary defense relevance. You're no longer tracking one object on a safe trajectory, you're potentially tracking multiple objects on uncertain trajectories. The anomalous photometry might be the first hint that something's not where it should be, because there are multiple somethings. This would justify Eowyn activation and intensive monitoring without requiring any exotic physics. Just straightforward Newtonian mechanics applied to a more complicated situation than initially realized. But if that's the case, why the silence? Fragmentation happens. Announcing that a comet broke into pieces and we're tracking all of them to verify their trajectories pose no threat sounds responsible rather than alarming. Unless the uncertainty is large enough that you can't yet rule out potential future Earth proximity for one or more fragments, then maybe you wait until better data narrows those uncertainty bounds before making public statements. Now push further into uncomfortable territory. What if the anomaly indicates unusual material properties or composition? Interstellar comets formed elsewhere, potentially under very different conditions than solar system objects. Different temperatures, different chemical abundances, different radiation environments. Could 3I Atlas contain exotic ices we don't normally encounter? Solid hydrogen or nitrogen, as proposed for Oumuamua, would sublimate at lower temperatures than water ice and produce no visible coma. If 3I Atlas has a mixed composition, conventional water ice-based outgassing models wouldn't predict its behavior accurately. Jets of invisible gas could create non-gravitational acceleration without producing detectable brightness changes. That would make astrometric predictions fail in exactly the way described. This isn't physics beyond current understanding, just chemistry we haven't directly observed in comets before. Confirming it would require spectroscopy detailed enough to detect the exotic molecules, which might be challenging if they're mixed with more common compounds. Again, scientists might prefer confirming such a hypothesis before publicizing it, knowing that exotic ice claims without solid evidence would invite skepticism. Now, enter truly speculative space. What if there's something artificial about 3I Atlas or part of it? Not necessarily an entire alien spacecraft, but perhaps technological debris, fragments of something built rather than naturally formed. Artificial materials could have density distributions, reflective properties, and thermal responses completely unlike natural rock and ice. That would break every model we use to interpret observations. Before dismissing this as absurd, remember that we still don't have satisfactory natural explanations for all of Oumuamua's behavior. Avi Loeb's artificial origin hypothesis remains unproven but also not definitively refuted. If interstellar space contains technological artifacts from other civilizations, whether ancient debris or active probes, occasionally one might pass through our system. The probability isn't zero. If scientists even remotely suspected artificial origins, secrecy becomes more understandable. The ramifications would be extraordinary. You'd want absolute certainty before making such a claim, because you only get to announce alien technology once in human history. Getting it wrong would destroy careers and institutional credibility. The burden of proof would be monumental. But here's the uncomfortable question. At what point does caution become cover-up? If evidence suggests something potentially artificial, who decides what threshold of confidence is required before informing the public? What if different experts disagree about interpretation? What if some see clear anomalies that can't be explained naturally while others insist we just need better models? Those internal disagreements could produce exactly the pattern we observe: intensive, coordinated monitoring without public communication. Keep gathering data while experts argue about interpretation. Don't say anything externally until consensus emerges internally. Meanwhile, the silence fuels speculation among those who notice the campaign's existence. Alternative physics offers another speculative avenue. What if interstellar? Comets interact with the interstellar medium or galactic magnetic fields in ways we don't understand. What if there are faint dark matter effects that become detectable only for objects that spent millions of years traversing interstellar space? These ideas sound fringe, but science occasionally gets surprised by phenomena that weren't predicted by theory. The problem with all these speculative hypotheses is they're essentially unfalsifiable without more data. You can't prove the absence of artificial components or exotic physics from current observations alone. You can only say current data doesn't require those explanations because simpler ones suffice. But absence of necessity isn't proof of absence, and that's what makes the Quiet campaign so intriguing to anyone inclined toward conspiracy thinking. The lack of information creates space for imagination. Every day without announcements becomes evidence that something is being hidden. Every technical bulletin that reveals nothing dramatic becomes proof they're controlling the narrative. Once distrust establishes itself, even eventual transparency can be reinterpreted as limited hangout, releasing carefully curated information while concealing the really interesting bits. I'm not arguing any of these speculative scenarios are true. Most are almost certainly false. But they illustrate how silence in the face of anomalies breeds speculation that fills the void with increasingly exotic possibilities. And some of those possibilities, however remote, intersect with genuine scientific questions worth investigating. Not because they're likely, but because if true, the implications would be profound. So maybe the improved astrometry methods aren't just about precision. Maybe they're about ruling out scenarios that sound too strange to mention publicly, but that nonetheless haunt the edges of scientific consideration. Maybe the campaign is methodically closing off alternative explanations, narrowing possibility space until only boring conventional physics remains. And only then, when all the weird scenarios are definitively excluded, do they issue the press release saying nothing unusual here, just a normal interstellar comet behaving as expected. Or maybe they find something that can't be excluded, can't be explained, can't be ignored, and then we discover whether institutions value transparency or control when confronted with the genuinely unknown. Part 9. Planetary Defense Network's Scope and Limits. The International Asteroid Warning Network operates at the intersection of science and policy, which means it navigates tensions between what's technically possible, politically acceptable, and publicly communicable. Understanding ORN's structure and mandate helps clarify whether using it for 3i Atlas stretches institutional boundaries or represents legitimate scope expansion. ORN emerged from recognition that asteroid impacts, while rare, pose civilization-threatening risk that no single nation can address alone. Impacts don't respect borders. An asteroid detected by American telescopes might threaten Europe. An impact in the ocean could generate tsunamis affecting multiple continents. Coordination isn't optional, it's necessary for effective response. The network's primary functions include detecting potentially hazardous objects, tracking their orbits with sufficient precision to assess impact probability, characterizing their physical properties to estimate potential damage, and communicating risk information to decision-makers and the public. When IAWN issues an alert, it triggers institutional responses. Additional observations get prioritized, orbital uncertainties get refined, mitigation options get evaluated. Most EON activity focuses on near-Earth asteroids, objects whose orbits bring them into Earth's neighborhood. These are categorized by size and minimum orbit intersection distance, the closest they could potentially pass to Earth if their orbit and Earth's orbit aligned perfectly. Objects larger than 140 meters that come within roughly 7.5 million kilometers qualify as potentially hazardous and receive special monitoring attention. So where does 3i Atlas fit? It's not a near-Earth asteroid. Its hyperbolic orbit means it's not gravitationally bound to the Sun and won't return. It's probably a few kilometers across based on brightness, making it substantial but not catastrophically large. Its closest Earth approach, if publicly available data is accurate, will be tens of millions of kilometers, far beyond any hazard threshold. On paper, this object doesn't meet normal IWN activation criteria, which raises questions about why the network is involved. One interpretation: the criteria are evolving. Perhaps after Oumuamua and Borisov, planetary defense planners decided interstellar visitors warrant monitoring regardless of technical threat level because they represent unknowns in our threat assessment models. This would be reasonable institutional learning if interstellar objects can behave unpredictably, if their orbits are harder to forecast accurately, if they might fragment or outgas in unusual ways. Then treating them as special cases requiring enhanced attention makes sense. You're not necessarily saying they're dangerous. You're saying they're insufficiently understood to be confident they're safe. That distinction matters for public communication. Saying we're tracking this because it might be dangerous sounds alarming. Saying we're tracking this because we don't fully understand it yet sounds cautious and prudent. But institutions often struggle to communicate that nuance effectively. Simpler to just activate monitoring protocols quietly, rather than try to explain evolving risk frameworks to public audiences looking for binary safe versus dangerous answers. There's also bureaucratic convenience in using existing networks rather than creating new ones. ORN already coordinates international observations, already has communication channels and data sharing protocols, already has scheduled meetings and decision-making procedures. If you need to organize global monitoring of any unusual object, whether or not it technically qualifies as a near-Earth threat, why build new infrastructure when you can use what exists? But using existing systems for expanded purposes without updating their official mandates creates policy drift. Eventually you have institutions operating outside their defined roles, taking on responsibilities that weren't formally authorized. That's not necessarily malicious or even problematic in the short term. Organizations adapt to circumstances, but it can lead to accountability gaps and oversight failures if the expansions go unnoticed or unremarked. Who authorized ILWN activation for 3I Atlas? That's not publicly documented. Presumably senior officials within NASA's Planetary Defense Coordination Office and equivalent bodies in other participating nations. But what criteria did they apply? What risk thresholds justified the resource commitment? Is there a documented decision-making process, or was this informal consensus among technical experts? These governance questions matter because planetary defense has potential dual-use implications. Technologies and networks developed for detecting and tracking asteroids could also track satellites, debris, or adversarial space assets. International coordination on space object monitoring touches on national security sensitivities. Transparency about decision-making processes helps ensure civilian scientific networks don't inadvertently become militarized or politicized. The long-term implications of treating interstellar visitors as planetary defense-relevant objects deserve consideration. If this becomes standard practice, every future interstellar detection triggers intensive monitoring campaigns. That might be good science, ensuring we characterize these rare visitors thoroughly, but it also diverts resources from other asteroid tracking activities that might have clearer hazard relevance. Telescope time is zero-sum. Hours spent observing 3I Atlas are hours not spent surveying for undiscovered near-Earth asteroids or following up on other recently detected objects. The planetary defense community constantly balances competing priorities: detection surveys to find new objects, follow-up observations to refine known orbits, characterization studies to understand physical properties. Adding interstellar visitors to that mix stretches finite resources further. You could argue interstellar objects deserve special priority because they're intrinsically more interesting scientifically. They provide unique information about other star systems, allow comparative studies of planetary formation processes, and potentially reveal exotic physics or chemistry not represented in solar system native populations. That's valuable science worth pursuing. But is it planetary defense science? Or is it astronomy that happens to use planetary defense infrastructure because that infrastructure exists and is capable? That distinction matters for budget justification and programmatic focus. If IR1 becomes a general-purpose observatory coordination network rather than specifically a threat monitoring network, its original mission could become diluted. These are not hypothetical concerns. Institutional mission creep is a well-documented phenomenon across governments and large organizations. Systems designed for specific purposes gradually expand into adjacent domains until they're doing things far removed from original intent. Sometimes that expansion is beneficial, bringing expertise and resources to bear on important problems. Sometimes it creates bloat, inefficiency, and loss of focus. For 3I Atlas specifically, the campaign might be entirely justified as a test case developing capabilities needed for future threat assessment. Or it might be overreach, applying planetary defense resources to a scientifically interesting but non-threatening object, because the justification for intensive monitoring wasn't strong enough without invoking the planetary defense framing. We can't judge without knowing the internal discussions and decision-making rationale, which brings us back to transparency. If NASA and IAN explained publicly why this campaign was structured as planetary defense activity, what criteria were applied, and what precedents it sets for future cases, then these questions would have answers. Instead, we have speculation based on fragmentary technical bulletins and inferential reasoning about institutional behaviour. Maybe after the wrap-up teleconference on February 3rd we'll get that explanation. Maybe papers will be published describing the campaign's scientific and operational outcomes, including discussion of how planetary defense networks should approach future interstellar visitors. That would close the loop, providing the context currently missing. Or maybe the campaign just ends quietly, results get filed away in technical archives, and the next interstellar visitor gets handled the same way with the same questions unanswered. Precedent established through repetition rather than policy deliberation. And we're left wondering whether planetary defense is evolving thoughtfully toward broader responsibilities, or drifting incrementally into mission spaces that deserve more explicit authorization and oversight than they're receiving. Part 10. If something did go wrong, scenarios and risk assessment. Let's engage in uncomfortable speculation, not prediction, not alarm, but systematic thinking about unlikely scenarios that nonetheless fall within physical possibility. If something about 3i Atlas presented actual risk, what might that look like, and how would response systems function? Start with fragmentation timing. Comets most commonly fragment near perihelion when thermal stress peaks. If 3i Atlas hasn't fragmented yet but will, the observation window might catch it happening. Fragments inherit velocity from the breakup event plus individual outgassing trajectories. If fragmentation occurred violently, perhaps driven by explosive sublimation of buried volatile pockets, pieces could scatter with significant relative velocities. Most fragments would follow trajectories similar to the parent body, spreading slowly along the orbital path like beads on a wire. But statistical mechanics says some pieces always get kicked in unusual directions. Low probability but non-zero. If an unlucky fragment got accelerated perpendicular to the original orbit, it could potentially cross into Earth's orbital neighbourhood months or years from now. Probability of such a fragment being large enough to matter and aimed precisely enough to threaten Earth is vanishingly small. Astronomical coincidences require multiple low-probability events to align, but vanishingly small isn't quite zero, and planetary defense exists precisely because improbable doesn't mean impossible. If campaign observations detect fragmentation and track multiple pieces, analysts would immediately begin orbital propagation for each fragment. Software takes current position and velocity, accounts for gravitational influences from sun and planets, propagates forward through time-generating probability clouds, showing possible future locations, where fragments might go, and when. If any probability cloud intersects Earth's orbit at times when Earth will be nearby, that fragment gets flagged for additional attention. More observations get requested to narrow its orbital uncertainty. If uncertainties remain large, precautionary measures might be considered. Not necessarily dramatic interventions, but perhaps alerting space agencies, adjusting satellite tracking, preparing contingency observation plans with radar systems that can provide extremely precise ranging if the fragment comes close enough. The decision tree branches rapidly. Confirmed fragment on potential Earth-intersecting trajectory triggers escalation to higher coordination levels. IAWEN would convene emergency consultations. National space agencies would brief their respective governments. Parallel tracks would begin, scientific refinement of trajectory predictions and policy preparation for possible public communication. Here's where things get complicated. At what uncertainty threshold do you inform the public? If a fragment has a 1 in 10,000 chance of Earth impact 6 months from now, is that significant enough to announce? 1 in 1,000? 1 in 100? There's no universal standard. Different agencies and governments have different risk communication philosophies. Announce too early with high uncertainty, and you risk unnecessary alarm followed by embarrassment when better data rules out the threat. Wait, too long and you're accused of cover-up when people eventually learn there was a possible risk you didn't disclose. Threading that needle requires judgment calls that vary by cultural context and political environment. The physical timeline matters too. Fragments from 3i Atlas wouldn't threaten Earth immediately. The comet is currently in the inner solar system, but on a trajectory that takes it outbound. Any fragments would follow similar paths and less dramatically perturbed. Closest possible approaches to Earth would likely occur months to years from now after complex orbital evolution. That time buffer allows for systematic response rather than emergency reaction. More observations to refine predictions. Analysis to characterize fragment sizes and compositions. Modeling to estimate atmospheric entry behavior if impact occurs. evaluation of whether any mitigation options exist, though realistically for an object detected this late, deflection wouldn't be feasible. You'd be limited to impact prediction and preparation. But even impact prediction has immense value. Knowing where and when a fragment might hit allows evacuation, disaster preparation, resource pre-positioning. A 10-meter fragment exploding in the atmosphere releases energy equivalent to multiple kilotons of TNT, like the Chelyabinsk meteor over Russia in February 2013. That event injured over 1,000 people from shattered glass and produced a shockwave felt hundreds of kilometers away. But with warning, casualties would have been zero. Close windows, stay away from glass, don't stand outside looking at the pretty fireball. Now escalate the scenario. What if instead of small fragments, 3I Atlas suffers catastrophic disruption, creating a debris field of hundreds or thousands of pieces? Probabilistically, some fraction would end up on trajectories intersecting Earth's orbit. Small pieces burn up harmlessly in atmosphere. Medium pieces create localized damage. Large pieces could be regionally catastrophic. This remains extremely unlikely. Comets don't often explode completely, but it's not physically impossible. Internal pressurization from rapid volatile sublimation, structural weaknesses from thermal cracking, rotational stresses from changing mass distribution. Various mechanisms could theoretically cause catastrophic fragmentation. If this occurred and was detected during the observation campaign, the response would shift from monitoring to crisis management. You'd immediately need orbital determination for every trackable fragment. Computational resources would be maxed out running simulations. Additional telescopes worldwide would be recruited for continuous tracking. Space-based assets like infrared satellites might be tasked if fragments were large enough and hot enough to detect. Simultaneously, internal government briefings would escalate. Space agencies would inform defense and emergency management authorities. Probabilistic threat assessments would flow upward through chains of command. Someone would have to decide when and how to inform the public, knowing that incomplete information creates panic, but withholding information creates conspiracy theories. International coordination would be essential and challenging. Different countries have different impact probabilities for different fragments. Who leads communication? Who coordinates response? These questions have been discussed in planetary defense planning exercises, but theory and practice differ. Political tensions that exist today don't disappear just because space rocks don't respect borders. Then there's the economic dimension. Even credible threat announcements without actual impacts can disrupt markets. Insurance costs spike. Travel patterns change. Resources flow toward preparation and away from normal economic activity. False alarms impose real costs. That creates pressure to avoid announcing unless certainty is very high. But waiting for certainty might mean waiting too long for effective response. Now pivot to a different unlikely scenario. What if the astrometric anomalies indicate not fragmentation, but unexpected orbital perturbation, something causing acceleration that models don't predict? If that acceleration happened to be pushing 3I Atlas even slightly toward Earth rather than away, uncertainty compounds. With natural comets, outgassing-driven acceleration is usually directed away from the Sun because that's where heating occurs. But jet orientations depend on nucleus geography and spin state. Unusual rotation or active regions at atypical latitudes could create jets that accelerate the comet in unexpected directions. Small changes accumulate over time. If campaign observations show the comet is accelerating toward Earth-crossing trajectories rather than safely away, that changes risk calculus even without fragmentation. You're now dealing with trajectory uncertainty in the most concerning possible direction. More observations become urgent. Radar facilities like Goldstone or Arecibo, if it were still operational, would be requested to provide precise ranging. The challenge is distinguishing low probability but non-zero threats from no meaningful threat situations. Probabilistic risk assessment gives you numbers: 1 in a million chance of impact, 1 in 10,000, 1 in 100. But humans don't process probabilities intuitively. We treat small risks as either negligible or catastrophic without much middle ground. Communicating nuanced probability to the public is notoriously difficult. Experts might say there's a 99.9% chance this fragment will miss Earth entirely. Headlines read, "Comet fragment could hit Earth." Technically, both statements are true. Practically, they communicate opposite messages. Managing that gap requires sophisticated risk communication infrastructure and public trust in institutions, both of which can be fragile. Then you add international dimensions. If fragments might impact specific regions, affected countries need notification. But giving different information to different countries breeds suspicion. Everyone demands the same data simultaneously. Yet detailed trajectory predictions near impact might reveal targeting information some nations consider sensitive for security reasons. You can predict impact locations. Could you also predict satellite positions or other strategic assets in near-Earth space? These complexities explain why planetary defense systems practice scenarios regularly through tabletop exercises and simulations. Organizations like NASA, ESA, JAXA, and others periodically run hypothetical impact scenarios to test coordination, decision-making, communication protocols. They identify gaps and friction points before facing real crises. But exercises can't perfectly replicate real-world pressures. Political considerations that participants politely sidestep in simulations become contentious in actual events. Media amplifies uncertainties. Social media spreads disinformation. Public psychology shifts from rational to emotional when personal safety feels threatened. The 3I Atlas campaign, if it were responding to actual detected risk rather than testing methods, would be operating under all those pressures but without acknowledging them publicly. Scientists would be working urgently while projecting calm. Governments would be briefed while official positions remained routine. Preparations would occur behind scenes while public-facing communications said nothing alarming. That scenario, hypothetical though it is, would look exactly like what we observe: coordinated intensive monitoring without public announcements. The silence wouldn't be casual scientific caution. It would be controlled information management until threat level becomes clear enough to communicate responsibly. I'm not suggesting that scenario is true. Almost certainly it isn't. The simplest explanation remains most likely. This is a straightforward scientific campaign testing improved measurement methods on a conveniently available unusual object, conducted quietly because scientists don't see sufficient public interest angle to warrant press releases. But exploring the what-if scenarios illustrates how planetary defense systems would function under pressure and why silence might be operational protocol rather than cover-up. Sometimes not talking is risk management, sometimes it's responsible caution, sometimes it's institutional habit, and sometimes, rarely, it's because saying nothing is safer than saying something incomplete. Distinguishing among those possibilities from outside requires information we don't have, which is precisely what makes silence so provocative to anyone inclined to question official narratives, and precisely why transparency, even uncomfortable transparency, acknowledging uncertainty, builds trust better than silence ever can. The observation window closes in late January. February 3rd brings the wrap-up teleconference. Whatever those telescopes have seen, whatever the data reveals, decisions will be made about what to say and when, and we'll discover whether the silence was justified or whether it was simply the path institutions chose because communication felt harder than saying nothing. Part 11. Recent news: AI-driven telescope data calibration. While 3I Atlas has been moving through our solar system with its quiet entourage of watching telescopes, the broader astronomy community has been undergoing a quiet revolution of its own. In October 2025, researchers published breakthrough results in applying artificial intelligence to telescope data calibration, achieving unprecedented precision in removing systematic errors that have plagued astrometry for decades. The work comes from a collaboration between European Southern Observatory teams and machine learning specialists at several universities. They trained neural networks on massive data sets from ESA's Gaia mission, teaching algorithms to recognize subtle patterns in how telescope measurements deviate from true positions. The networks learn to identify and correct biases caused by atmospheric distortion, detector imperfections, optical aberrations, and other systematic effects that traditional calibration methods struggle with. What makes this relevant to 3I Atlas is timing and capability. These AI calibration tools became operationally ready just months before the November kickoff meeting. The phrase, improved astrometry methods, appearing in the campaign bulletin suddenly gains concrete meaning. This isn't vague aspiration about better measurements. It's likely direct reference to deploying these newly validated AI-driven calibration pipelines in real-world high-stakes observations. The technical achievement is genuinely impressive. Traditional astrometric calibration relies on comparing your target object against reference stars of known position. You assume stars provide fixed anchor points, though in reality they move slowly, and their catalogued positions have uncertainty. You apply geometric transformations accounting for atmospheric refraction, based on models of how Earth's atmosphere bends light at different elevations and wavelengths. You correct for detector biases using calibration frames taken with uniform illumination sources. But residual errors always remain. Maybe your atmospheric model doesn't perfectly capture turbulence conditions on a particular night. Maybe your reference star catalogue has small systematic errors at certain magnitudes or colours. Maybe detector aging has changed pixel response in ways your standard calibration doesn't capture. These residuals typically scatter randomly, averaging out over many observations. But for unusual objects like comets, where you're trying to measure photometric centroids of extended diffuse sources, those residuals can masquerade as real effects. The AI approach sidesteps explicit modelling. Instead of writing equations describing how atmosphere refracts light, you show the algorithm thousands of examples where you know the true position and let it learn whatever pattern recognition necessary to correct observations to match truth. Neural networks excel at finding complex nonlinear relationships in high-dimensional data that humans can't easily write down mathematically. The October 2025 results demonstrated improvements of 20 to 30% in astrometric precision for faint extended objects compared to classical methods. That margin could be the difference between confidently detecting non-gravitational acceleration in a comet's motion versus having that signal lost in measurement noise. It could be the difference between correctly identifying centroid offsets versus attributing them to calibration error. If the 3i Atlas campaign is using these tools, the observation program becomes dual purpose. Scientifically, you're characterizing an unusual interstellar comet. Operationally, you're conducting live validation of AI-driven astrometry under real-world conditions with a challenging target. Success would prove the methods work beyond controlled test environments, paving the way for routine deployment. This also explains why multiple observatories matter. Neural networks improve with diverse training data. Each telescope has unique characteristics, different optics, different detectors, different local atmospheric conditions. An algorithm trained to correct errors across that diversity becomes more robust and generalizable. The coordination isn't just about redundancy, it's about feeding the AI information from varied contexts to refine its learned corrections. There's fascinating synergy here between artificial intelligence and astronomical observation. Machine learning requires massive labeled datasets, situations where you know the right answer and can train algorithms to reproduce it. Astronomy generates enormous data volumes but usually lacks ground truth labels. You don't know the true position of a newly discovered comet, so how do you train an algorithm to measure it correctly? The clever solution uses synthetic data and historical objects with precisely known orbits. You generate simulated images of comets with known properties, process them through your observation and analysis pipelines, compare measured positions against true positions, and train algorithms to correct the deviations. Then you validate on real comets whose orbits have been refined by years of observations. If your AI-corrected measurements of those well-known objects match their established positions better than classical methods, you've validated the approach. 3i Atlas becomes a live test case for a different reason. It's exhibiting anomalies that challenge interpretation. Is the photometric centroid genuinely offset from predicted positions due to real physical causes, or is it calibration error that traditional methods don't handle well for objects this faint and diffuse? Apply your AI calibration tools. If the anomalies persist after applying the best corrections available, you've ruled out instrumental error as explanation. What remains must be physically real. That's powerful. It transforms uncertain interpretation into confident conclusion, and it demonstrates operational capability to funding agencies and mission planners considering future planetary defense infrastructure investments. You can say we have AI-augmented astrometry that achieves X precision for objects of type Y under condition Z, validated through campaign ABC. That's the kind of concrete performance metric that justifies budget allocations for next-generation systems. The geopolitical dimension shouldn't be ignored. Multiple nations and space agencies participate in IAWN and planetary defense activities. Demonstrating advanced AI-driven capabilities that significantly outperform classical methods establishes technological leadership. It shows that investments in machine learning R&D pay off with practical operational advantages. For spacefaring nations competing for influence and prestige, these demonstrations matter. There's also a timeline correlation worth noting. The 3i Atlas campaign observation window runs through January. The AI calibration results were published in October. That's barely time to operationalize the new techniques, train personnel on new software pipelines, debug deployment issues, and coordinate usage across multiple observatories. The compressed timeline suggests urgency. Why rush new methods into operation unless there's compelling reason to achieve maximum precision as quickly as possible? Maybe that reason is purely scientific opportunity. You have an unusual interstellar comet available for observation. You have new tools that could extract better science than ever before possible. You coordinate immediately to capitalize on the opportunity before the comet fades out of range. Or maybe the anomalies appeared in early reconnaissance observations, creating immediate need for better measurements to determine whether they're real or artifactual. Rush the AI tools into deployment specifically to resolve that question. The campaign becomes troubleshooting exercise as much as science program. Either way, we're watching the future of astronomy emerge. Artificial intelligence isn't replacing human astronomers. It's augmenting human capabilities, handling tedious calibration and error correction tasks more precisely than classical methods, while freeing astronomers to focus on scientific interpretation. The partnership between human insight and machine pattern recognition achieves results neither could accomplish alone. And if this campaign succeeds, if the AI-driven astrometry definitively characterizes 3i Atlas and resolves its anomalies, it establishes template for future observations. Every subsequent unusual object gets the same treatment. Standard protocol becomes detect object, mobilize observatories, apply AI-calibrated astrometry, rapidly characterize behavior, assess any risk, communicate results. The entire pipeline optimized for speed and accuracy. We might look back at 3i Atlas as the case that validated the system, the trial run before the methods became routine, not famous for what the comet was, but famous for how it was studied, the moment planetary defense entered its AI-augmented era. Or we might look back at it for entirely different reasons if those AI-augmented observations reveal something genuinely unexpected that no amount of algorithmic correction can explain away. Something physically present in the data that demands explanation beyond conventional comet behavior. February 3rd approaches. The algorithms are processing data even as I speak, and somewhere in server farms, neural networks are learning patterns in photon distributions captured by telescopes watching a visitor from another star. Part 12. Recent news. New exoplanet discovery this month. For contrast, consider how differently astronomy handled another recent discovery. On October 15, 2025, the TESS mission team announced detection of a new potentially habitable exoplanet orbiting a nearby star. TESS, the Transiting Exoplanet Survey satellite, found what appears to be a rocky world roughly 1.3 times Earth's mass, orbiting in the habitable zone of a red dwarf star just 42 light-years away. The announcement came with everything you'd expect from a significant astronomical discovery. NASA issued a press release with artist renderings showing what the planet might look like based on its estimated properties. The principal investigator gave quotes about how exciting this find is and what it means for the search for life beyond Earth. Multiple news outlets covered the story. Science journalists explained why habitable zone planets around red dwarfs are particularly interesting targets for biosignature detection, with upcoming telescopes like James Webb. Within days, the discovery appeared in mainstream news, science magazines, astronomy podcasts, and social media discussions. The public conversation included accessible explanations of transit photometry, how scientists determine planet masses and orbits, why this particular star system is interesting, and what follow-up observations are planned. Complete transparency, enthusiastic communication, active engagement with public interest. Now contrast that with 3i Atlas, an interstellar visitor, only the third ever confirmed, exhibiting anomalous behavior unusual enough to warrant a 2-month coordinated planetary defense level observation campaign across multiple international facilities. That's arguably more rare and potentially more significant than one more exoplanet among thousands discovered. Yet, no press release, no artist renderings, no principal investigator quotes, no mainstream coverage. Just a technical bulletin that almost nobody outside professional astronomy would ever see. The difference is stark. Why does one discovery get the full public engagement treatment while the other gets silence? Several possible explanations exist, none entirely satisfying. First, exoplanets are safe. They're light years away. They can't threaten Earth. They represent pure scientific discovery without any risk component. That makes communication straightforward. There's no chance your announcement will cause alarm. You're only delivering good news about expanding human knowledge of the cosmos. Second, exoplanet discoveries have established public relations frameworks. The test team has media coordinators, prepared graphics, relationships with science journalists, experience crafting narratives that engage lay audiences. When a discovery happens, machinery exists to publicize it efficiently. The process is routine, even if each individual discovery is exciting. Third, exoplanets align with NASA's strategic messaging about searching for life beyond Earth. Potentially habitable worlds feed into that narrative beautifully. They justify continued investment in space telescopes and astrobiology research. They inspire public imagination. They're exactly the kind of story that builds support for space science programs. 3i Atlas fits none of those patterns. It's not provably safe because it exhibits unexplained behavior. It doesn't have established publicity machinery because interstellar objects are still novel enough that protocols don't exist. It doesn't obviously support strategic messaging because planetary defense is harder to communicate than exoplanet exploration. Threat assessment creates anxiety, whereas discovery creates wonder. But that logic only holds if you assume institutions optimize for message control rather than truth-telling. A more transparent approach would be to communicate everything using frameworks appropriate to each case. For safe distant discoveries, celebrate the science. For uncertain nearby objects, explain the monitoring process and why caution is prudent. Trust the public to handle nuanced information instead of assuming they'll panic. The exoplanet announcement included uncertainty. Scientists acknowledge they don't yet know the planet's atmosphere composition, whether it has water, whether conditions truly permit life. That honest acknowledgement of unknowns didn't prevent public engagement. It made the story richer by explaining what questions remain and how future observations might answer them. Applying that same transparency to 3i Atlas would sound like, we're conducting intensive observations of an unusual interstellar comet that's showing behavior we don't fully understand yet. It exhibits photometric anomalies that could indicate several things from fragmentation to asymmetric outgassing. We're using improved measurement techniques to characterize what's happening. There's no indication of danger, but thorough monitoring is prudent when dealing with objects whose behavior doesn't match predictions. We'll share results once analysis is complete. That statement is honest, informative, and not alarming. It invites interest without creating panic. It acknowledges uncertainty without suggesting cover-up. Why not use it? Perhaps because crafting and delivering such communication requires effort and coordination that nobody felt was justified for what they consider routine observations. Perhaps because institutional culture defaults to saying nothing, rather than saying something that requires careful calibration. Or perhaps because the exoplanet comparison reveals something uncomfortable. Space agencies enthusiastically communicate when they control the narrative, but retreat into silence when faced with anomalies they haven't fully characterized. Positive stories about human capability to explore the cosmos get amplified. Uncertain stories about things behaving unexpectedly get suppressed until they resolve into either explanations or non-events. That pattern, if true, suggests institutions value reputation management over public engagement. They'll share wins but hide uncertainties. Over time, that erodes trust because people notice what isn't communicated as much as what is. Selective transparency creates suspicion that information is being filtered through institutional interests rather than presented objectively. The timing makes the contrast even sharper. The exoplanet announcement came October 15th. The 3i Atlas campaign kickoff meeting happened October 10th, with observations starting November 27th. These aren't ancient history, they're concurrent developments in ongoing astronomy programs. Yet one gets celebration, while the other gets silence. Imagine if NASA's approach were reversed. Imagine quiet technical bulletins about exoplanet detections, while launching massive public campaigns about interstellar comet monitoring. The public would justifiably ask why the priorities seemed inverted. They'd wonder whether focusing attention on comets meant hiding something concerning. The actual communication pattern, celebrating distant discoveries while quietly monitoring nearby anomalies, creates similar questions with opposite valence. None of this proves anything nefarious about the 3i Atlas campaign. The most likely explanation remains that scientists are conducting observations they consider moderately interesting, but not sufficiently unusual to warrant publicity. No conspiracy necessary, just different threshold judgments about what rises to public announcement level. But the comparison to exoplanet communication highlights that those thresholds aren't purely objective. They're shaped by institutional culture, strategic messaging priorities, and comfort levels with different types of public engagement. And when one type of discovery consistently gets amplified while another type gets suppressed, patterns emerge that invite scrutiny. February 3rd will bring the wrap-up teleconference. Maybe afterwards, results get published with full transparency about what was found and why the campaign was structured as it was. Maybe not. But either way, the contrast with how other astronomy gets communicated will remain relevant for anyone trying to understand how institutions choose what to share and what to keep quiet, and whether those choices serve science, serve institutions, or serve something else entirely. Part 13. Recent News, Space Weather Event Impacting Observatories. October 2025 brought another complication that might be relevant to the 3i Atlas campaign, a significant geomagnetic storm that disrupted astronomical observations globally. On October 24th through 26th, a series of powerful coronal mass ejections from the Sun triggered aurora displays visible as far south as the Mediterranean and northern United States. Beautiful for skywatchers, problematic for astronomers. Geomagnetic storms create radio interference that disrupts communications between observatories and satellites. GPS timing systems, critical for precise astrometry, experience errors during intense geomagnetic activity. Atmospheric ionization affects how light propagates from space through Earth's atmosphere, introducing additional distortion beyond normal atmospheric turbulence. For telescopes trying to achieve maximum precision, these events are operational nightmares. The October storm reached G4 severity on Noé's scale, where G5 is the most extreme. At that level, power grid operators worry about transformer damage. Satellite operations get degraded. Radio communications suffer blackouts at certain frequencies, and ground-based astronomical observations become significantly more challenging. For context, the most recent comparable geomagnetic storm before this was in May 2024, also driven by strong solar activity. That event similarly disrupted observations and created spectacular low-latitude auroras. The Sun operates on an approximately 11-year activity cycle, and we're currently approaching solar maximum, the period of peak sunspot numbers and most frequent explosive events. This means geomagnetic disturbances will likely continue through 2026 at elevated frequency compared to solar minimum periods. The 3i Atlas observation window from November 27th through January 27th sits squarely in this active period. Additional storms are statistically likely during those 2 months. How does this impact the campaign? Most directly, storms cause observation outages. When geomagnetic conditions deteriorate, telescopes may stop observing because data quality becomes unacceptably poor. You can't gather useful astrometric measurements when the atmosphere is electrically disturbed and GPS timing is unreliable. Better to wait for conditions to improve than waste telescope time on corrupted data. But you can't predict when storms will occur more than a few days in advance. Coronal mass ejections are visible leaving the Sun, giving roughly 2 to 3 days warning before the charged particles reach Earth. Solar flares, which often accompany CMEs, affect Earth within minutes via electromagnetic radiation. Neither permits long-range scheduling. You might plan observations weeks ahead, only to have space weather render them impossible. This unpredictability necessitates flexible scheduling and redundancy. If one observatory gets weathered out, terrestrially or magnetically, others at different locations might have clearer conditions. The global coordination of the 3i Atlas campaign provides resilience against these disruptions. When Hawaii is under geomagnetic storm effects, maybe Chile is less affected. When everyone is affected, you accept the gap and resume when conditions improve. There's another subtler effect worth considering. Could space weather explain some of the anomalous behavior being attributed to 3i Atlas itself? Geomagnetic storms affect Earth's upper atmosphere and ionosphere, regions through which starlight passes before reaching telescopes. Unusual atmospheric conditions could create apparent positional shifts or photometric variations that actually originate in Earth's atmosphere rather than from the comet. Careful observers account for atmospheric effects through standard calibration procedures. You observe reference stars alongside your target, measure how their positions differ from catalogued values, apply corrections assuming the target experiences similar distortions. But comets aren't point sources like stars. Extended diffuse objects might respond differently to atmospheric perturbations than sharp stellar images do. If the 3I Atlas anomalies correlate with geomagnetic activity levels, that would suggest atmospheric artifact rather than genuine comet behavior. Conversely, if anomalies persist independent of space weather conditions, that rules out atmospheric explanation and points towards something intrinsic to the object. This is precisely the kind of systematic effect analysis that careful multi-observatory campaigns allow you to investigate. The improved astrometry methods mentioned in the campaign bulletin might include specific techniques for handling space weather-degraded observations. Maybe the AI calibration algorithms discussed earlier are trained to recognize and correct for ionospheric effects that classical methods miss. Testing those algorithms under challenging conditions would validate their robustness for future operational deployment. From a scheduling perspective, the campaign organizers likely factored space weather risk into their planning. The observation window extends over 2 months partly to ensure adequate total observation time, even accounting for predicted weather losses and space weather disruptions. You build in redundancy, anticipating some fraction of scheduled observations will become impossible. The specific dates chosen might reflect optimal balance between comet brightness and predicted solar activity levels. Still, there's inherent uncertainty. A particularly severe geomagnetic storm, say G5 level, could wipe out a week or more of observations globally. If that happened during a critical period when the comet was undergoing rapid changes, you might miss important events. That risk can't be eliminated, only mitigated through responsive rescheduling and opportunistic observation when conditions permit. There's also a communication dimension. If space weather significantly disrupted the campaign, would that be communicated publicly? Probably not unless someone specifically asked. It would appear in technical papers as acknowledgement that weather limited data quality or temporal coverage. But it wouldn't warrant press releases. Most people don't care about operational challenges of astronomical observations unless those challenges affect scientific conclusions. Yet for anyone trying to understand why this campaign is structured as it is, space weather context matters. It explains why you need multiple observatories, why the observation window is generous, why careful calibration is essential. It's part of the mundane operational reality behind any major observing program, and it reminds us that Earth itself is not a passive platform. We're on a planet orbiting an active star within a magnetosphere that's constantly buffeted by solar wind and occasionally slammed by explosive solar events. That dynamic environment affects every observation we make of the cosmos beyond our atmosphere. Achieving precision requires accounting for all those effects, separating signal from noise introduced by Earth's own restless context. The October storm has passed. Solar activity continues. More storms will come. The telescopes will keep watching when they can, pausing when they must, gathering data point by precious data point. And somewhere in the accumulated observations, patterns will emerge that either explain the anomalies or deepen the mystery. Either way, we'll understand a little more about how interstellar visitors behave and a little more about the challenges of watching them from our electromagnetically noisy planet. Part 14. Recent News. Advances in Interstellar Object Theories. While 3I Atlas has been the focus of intensive observation, theoretical astrophysicists haven't been idle. In September 2025, a significant paper appeared in Nature Astronomy, proposing new mechanisms for how interstellar objects interact with the interstellar medium and galactic environment during their millions of years traveling between stars. The research, led by teams at University of California, Santa Cruz and Max Planck Institute for Astronomy, suggests that interstellar comets might accumulate an electrically charged surface layer through prolonged exposure to cosmic rays and galactic magnetic fields. This charging could persist even after entering a solar system and affect how the comet interacts with solar wind and radiation pressure. The implications are fascinating. A charged comet nucleus would respond to magnetic fields in ways neutral objects don't. The solar wind carries magnetic field lines spiraling outward from the Sun. A charged object moving through those fields experiences forces beyond simple gravity. These electromagnetic effects would be tiny, but accumulated over weeks or months, they could produce detectable non-gravitational acceleration. Moreover, charged surfaces might influence outgassing behavior. When ice sublimates, gas molecules can carry electric charge with them. If the nucleus has net charge, this creates an electric field that affects how gas expands away from the surface. You might get preferential outgassing directions or velocities that differ from purely thermal expectations. That would create asymmetric comal structure and photometric complexity. This theoretical framework could explain aspects of Oumuamua's mysterious acceleration without requiring exotic hydrogen icebergs or artificial light sails. A normally composed comet with charged surface layers might accelerate detectably while producing minimal visible coma if the charged outgassing is predominantly in transparent gases rather than reflective dust. For 3I Atlas, if this theory is correct, the photometric anomalies might trace to charged particle interactions, creating brightness distributions that don't align with simple gravitational predictions. The centroid offsets could result from electromagnetic forces pushing gas and dust asymmetrically in ways current models don't account for. The September paper provides testable predictions. Charged comet behavior should correlate with solar wind conditions and interplanetary magnetic field geometry. When the comet passes through regions of stronger or differently oriented magnetic fields, its apparent position and brightness distribution should shift in predictable patterns. If 3I Atlas observations capture such correlations, that would constitute strong evidence for the charged surface hypothesis. This also highlights how rapidly theoretical understanding is evolving. 5 years ago, before Oumuamua, nobody seriously considered electromagnetic effects on comet dynamics. Gravitational models and simple rocket effect outgassing seemed sufficient to explain observed behaviors. The interstellar visitors challenged that complacency by behaving in ways those models couldn't accommodate. Now we're seeing theoretical catch-up. Multiple research groups are exploring previously neglected physics that might matter for objects with different histories than solar system native, comets. The September paper is one example. Others have proposed that interstellar comets might contain supervolatile ices that our local comets lack because they formed in colder environments around less luminous stars. Different ices mean different sublimation behavior and different non-gravitational forces. There are also proposals about radiation damage. Cosmic rays passing through ice create chemical changes, breaking molecular bonds and creating unusual compounds. An interstellar comet spending millions of years in the galactic environment accumulates significant radiation dose. Its surface composition might be heavily processed, perhaps forming an insulating crust that affects heat conduction and outgassing patterns. All these theoretical advances share a common theme. Interstellar objects are not just curiosities, they're probes of conditions and processes we can't otherwise study directly. We can't travel to other star systems to collect samples, but when samples come to us, even briefly, we can learn about environments and chemistry occurring in parts of the galaxy we'll never directly visit. That makes detailed characterization of 3I Atlas scientifically valuable beyond simple orbital determination. If it confirms predictions of charged surface theories, or reveals unexpected compositional properties, or demonstrates outgassing behavior influenced by radiation damage, those discoveries inform our understanding of galactic scale processes. You're not just studying one comet, you're studying the galaxy itself through the comet as intermediary. This broader context might partly explain the intensive observation campaign. Maybe scientists recognize that interstellar visitors provide unique scientific opportunities that justify significant resource allocation, regardless of planetary defense considerations. The urban infrastructure happens to exist and enables the coordination needed. Using it doesn't necessarily mean threat assessment is the primary motivation, but that reading requires assuming the planetary defense framing is incidental or secondary, which sits awkwardly with how the campaign was structured and announced. If pure science were the driver, you'd expect different institutional organizations and funding sources. Using OWN specifically suggests threat-related justification was necessary, even if actual threat is remote. Perhaps the reality is hybrid. Scientists want to study this object intensively because it's scientifically valuable. Getting resources allocated requires framing that justifies priority access to expensive telescope time. Planetary defense provides that justification even if actual defense concerns are minimal. The framing becomes instrumental, a means to enable science that might not otherwise happen. That dynamic, if true, isn't necessarily cynical. Scientists work within systems that require justifications matching institutional priorities. If planetary defense funding supports observations that yield valuable pure science alongside operational capability development, that's arguably efficient use of resources. But it does blur lines between defense and research in ways that make communication tricky. How do you announce a planetary defense campaign that's really mostly science without either misrepresenting the science or undermining the defense framing that enabled the resource allocation? Simpler to say nothing, conduct the observations, publish scientific results in appropriate journals, and let institutional stakeholders sort out messaging to their respective constituencies. That might be exactly what's happening. Not sinister cover-up, but pragmatic navigation of institutional complexities that outsiders don't fully appreciate. The silence isn't hiding danger. It's avoiding conversations about resource allocation priorities and organizational mandates that would distract from simply doing the science. Or I'm being too generous, constructing benign explanations when simpler reading is that institutions prefer opacity to transparency, when the latter requires explaining uncomfortable details. The truth probably lies between those extremes, as truth usually does. What matters for our story is that theoretical understanding of interstellar objects is advancing rapidly, driven partly by observations of Oumuamua and Borisov, partly by anticipation of many more detections as survey capabilities improve. 3i Atlas arrives at a moment when theory has matured enough to make specific predictions that observations can test. If the campaign confirms charged surface theories, or reveals other unexpected physics, it becomes landmark case study demonstrating how observations and theory advance in dialogue. If observations rule out those theories, that's equally valuable, narrowing possibility space and forcing theorists back to reconsider assumptions. Either way, by February 3rd, when the wrap-up teleconference occurs, we'll have data capable of constraining or refuting multiple theoretical proposals about interstellar object behavior. Part 15. Recent news. 5. AI. LLM. Simulation tools in astronomy planning. In February 2025, a team at the European Space Agency unveiled something that sounds like science fiction but is already reshaping how we watch the sky. They call it AstroGuard, and it is not a telescope or a satellite. It is an artificial intelligence system that learned to schedule observations, assess mission risks, and flag anomalies in real time by reading through decades of astronomical data, mission logs, and even natural language reports from observatories around the world. The system can coordinate hundreds of telescopes across multiple continents, predicting when and where to look based on uncertainty models that would take human schedulers weeks to calculate. This is not some distant future we're talking about. This is happening now as you listen to these words. AstroGuard represents a fundamental shift in how we respond to cosmic threats. Traditional observation planning relied on committees, email chains, and manual calculations to coordinate follow-up observations of interesting objects. If something unusual appeared in the night sky, astronomers would file a circular, other teams would read it hours or days later, and slowly a coordinated response would emerge. That system worked reasonably well when we had fewer telescopes and fewer objects to track. But we are drowning in data now. Every night, automated surveys detect thousands of moving objects, variable stars, potential supernovae, and asteroid position updates. The sheer volume has exceeded what human coordination can effectively manage. This is where machine learning enters the picture, not as a replacement for astronomers, but as a force multiplier. AstroGuard and similar systems can ingest observation requests from multiple sources, evaluate weather predictions across dozens of sites, calculate optimal viewing windows based on object trajectories, and even assess the scientific priority of competing targets. When an unusual object is detected, the system can automatically trigger follow-up observations at telescopes best positioned to capture critical data. It learns from past campaigns, recognizing patterns in how objects behave and identifying statistical outliers that might warrant immediate attention. The practical applications are already transforming how we respond to potentially hazardous asteroids and comets. Imagine a newly discovered near-Earth object with an uncertain orbit. Traditional methods would involve calculating error ellipsoids, manually checking which telescopes have available time, and coordinating observations through human schedulers across different institutions and time zones. An AI system can do this in minutes, running thousands of simulated trajectories to identify which observations would most reduce orbital uncertainty, then automatically proposing observation schedules to participating facilities. Some systems even draft the technical justifications for telescope time requests, translating orbital mechanics into plain language that allocation committees can quickly evaluate. Now apply this capability to something like 3I Atlas. The comet arrived with massive uncertainties, both in its orbit and its physical properties. Human astronomers made educated guesses about optimal observation times, but they were working with incomplete information and limited coordination tools. An AI-assisted system could have run uncertainty propagation simulations continuously, predicting how the comet's position errors would evolve over time and identifying critical observation windows where even brief measurements would dramatically improve our knowledge. It could have coordinated observations across wavelengths, ensuring that infrared telescopes, optical telescopes, and radio arrays were all gathering complementary data during the same viewing windows. More importantly, these systems excel at anomaly detection. They establish baseline expectations for how objects should behave, then flag deviations that fall outside normal parameters. If 3I Atlas suddenly brightened unexpectedly, or if its trajectory showed deviations inconsistent with gravitational models, an AI monitor could alert human astronomers within hours instead of waiting for someone to manually notice the discrepancy in the data. This is particularly crucial for non-gravitational effects, those subtle accelerations from outgassing or other forces that require careful analysis to detect. Machine learning algorithms trained on thousands of comet trajectories can spot the signature of anomalous acceleration far faster than manual inspection. The potential goes beyond just observation scheduling. Large language models, the same technology behind conversational AI, are being trained on astronomical literature to assist with rapid literature reviews and hypothesis generation. When faced with an unusual observation, an astronomer might ask the system to summarize all previous instances of similar behavior, identify relevant theoretical papers, or even suggest observational tests that could distinguish between competing explanations. This does not replace scientific thinking, but it accelerates the process of connecting new observations to existing knowledge. Imagine having an infinitely patient research assistant who has read every astronomy paper ever published and can instantly recall relevant precedents. Some researchers are already using these tools for planetary defense simulations. They run thousands of scenarios where hypothetical objects are discovered at various distances and trajectories, testing how quickly we could characterize the threat and coordinate a response. The AI systems identify bottlenecks in our current capabilities, revealing scenarios where we would struggle to gather necessary data in time. These are not abstract exercises. They are stress tests for our planetary defense infrastructure, revealing gaps we need to address before a real emergency arrives. The integration of AI into astronomy is still in its early stages, but the trajectory is clear. Within a few years, every major observatory will likely have some form of intelligent scheduling assistance. Surveys will automatically trigger coordinated follow-up campaigns when interesting targets are detected. Anomaly detection systems will scan data streams in real time, flagging unusual behavior before human analysts even see the raw data. And natural language interfaces will let astronomers query complex datasets and coordinate observations using plain English rather than specialized commands. Here is where 3I Atlas becomes more than just another interstellar visitor. If this comet begins behaving strangely, if those non-gravitational forces start showing patterns we cannot explain, we might witness the first major planetary defense event managed partly by artificial intelligence. The tools are in place now. The systems are learning. And if 3I Atlas decides to surprise us, we will have a front-row seat to the future of cosmic surveillance. What if this object, this frozen messenger from between the stars, becomes the test case for a new era? What if future historians look back and identify the 3I Atlas campaign as the moment when humanity stopped relying solely on human intuition to protect Earth from cosmic threats? We are standing at that threshold now, and we do not yet know which side of history we will land on.